Hey guys, this week we are going to talk about 2.6 in the textbook, concavity. So before we get into concavity, we need to talk about what interval notation is. So how do we describe sets in interval notation or sets of numbers? So the question I have for you is, how can we describe all numbers less than -1? Well, typically what we would do is we would just assign a variable, say x, and I would say that x is less than -1. And this describes the set of all numbers less than -1. And the way that I denote this on the number line is, first of all, I put an open circle because this is strictly less than, there's no line underneath it. I put an open circle at -1, and to denote every single number that's less than -1, I shade to the left because those are all the numbers less than -1. And then this goes all the way out to -infinity. Okay, pretty cool. So we have this huge infinite set of numbers. X is less than -1. Now, how do we say this in interval notation? The way that we say it is we start at our lower bound, and we're not including it because we never include -infinity or infinity. And we use a parentheses to indicate that we don't include that. So we're starting at -infinity, and we're going all the way up until -1. And we're not including -1 because we want everything strictly less than -1, not including it. So to denote that, we have a parentheses. And both of these sets simultaneously represent the set of numbers that are smaller than -1. All right, so this is a little cheat sheet. If you have less than or equal to or greater than or equal to, you use brackets and closed circles instead of what we just did, which was parentheses and open circles for greater than or less than. And then this guy means union, this big U. And basically that means that we're joining sets of numbers. And we're going to do an example with that just to show you guys how we can do that. All right, so directions say plot this on the number line, then write the set of numbers in interval notation. So what does this guy say? This guy says all numbers bigger than or equal to 4. So here's our number line. And I am, I'm lazy, okay, as some of you guys will know. So if I don't have to write a lot of numbers, I don't, but I will for these. If I was to just do this on my own, I'd probably just put 4 on the number line and then do the stuff. But just to illustrate a point, I'm going to put a closed circle because of the line underneath that says we include 4 in the set. We're not excluding it. So I'm putting a closed circle at 4. And this says everything bigger than 4, right? We read variable first. So everything bigger than 4. That means we shade to the right all the way out to +infinity. All right, so in interval notation, we start at 4 and we include it. So we put the bracket there. And we go all the way up to +infinity. Parentheses. We don't include infinity ever. So that is an interval notation. Let's do another one. X is strictly less than 6. So here I'm going to start to show you guys how I'm lazy. I'm putting 6 on the number line, and -infinity goes that way, and infinity goes that way. And I want to shade everything strictly less than 6, which means we don't include it. So we put an open dot there. 6 is not in our set. But everything to the left of it is. So how about 5.9999999? Is that included? Yeah, it's included. It's not 6. So anything directly to the left of 6 is included in that set. How do we say it in interval notation? Well, what's the lowest number we start with in this orange set? We start with -infinity. And we go all the way up to x equals 6. And we don't include it. And that's what the parenthesis is there for. All right, let's look at this next example. So we have x is sandwiched between 1 and 4. So we can say that starting if we were to read this out loud, we would start with x, and we would say x is greater than 1, right? Because the sign is opening towards x, so we say x is greater than 1. And then the second part, again, we're starting with the variable. We say x is, since the point is facing towards x, this is less than. X is less than, since it has a line under it, it's less than or equal to 4. All right, so that's how we say that in words. X is greater than 1, and x is less than or equal to 4. So basically, the set is going to be sandwiched between 1 and 4. So here's 1, here's 4. With 4, we have a closed dot because of the less than or equal to next to it. And for 1, we have an open dot because of the strictly greater than sign. And x is sandwiched between these guys. So all we're going to do is shade between that to illustrate this set right here. X is greater than 1, and x is less than or equal to 4. All right. So how do I write this in interval notation? Well, I want to start at my lowest value, which is 1, but not including 1. So I start at 1 with the parentheses, and I'm going all the way up until x equals 4, and I do want to include this in my set because of, again, this less than or equal to. So any number between 1 and 4, not including 1, is in this set, as you can see in yellow. So this is my answer in interval notation. So let's do this other example. We have x is less than -1 or x is greater than 2. So either of these could be true. In the previous problem, they since it was between the two numbers, they simultaneously had to be true. Like it had to be greater than 1, but less than and equal to 4 at the same time. Here, however, let's put our numbers on the number line. We have -1 and we have 2. So x is less than 1. Well, this is going to be an open dot because it's strictly less than. And I'm shading to the left because, again, less than. And this is going all the way to -infinity. Or, so this could be in our set, or x is greater than or equal to 2. So this time I have a closed dot because of the line under the greater than sign. And since it's going to be everything greater than 2, I shade to the right. So everything in red and purple is in this set. Now, how do I write this set in interval notation? Well, I got to use the union because I don't want to include all of this stuff in yellow. I don't want to include that. So I need to separate my sets out. The first set is going to be, I start at -infinity, and I include all the numbers up until -1, but not including -1. All right. Then I gotta union that with this other set in purple. Right? I don't want it to be one big parentheses because that would include this stuff that we don't want in yellow. All right. So I gotta union this with 2 all the way up to +infinity. All right. And so that is going to be the set in interval notation. So before we get into what we're supposed to be talking about, which is concavity, I want to remind you of what slope is. So in this lecture, I'm going to use the words rate of change in replacement of slope. Okay, so whenever I say rate of change, think slope. All right, that's just a more sophisticated way of talking about slope, and it's going to come up if you take calculus and again in this class later on. So what is slope? We can think of slope in a few different ways. the first way that people think about it is rise over run. So like you're given 2 points and you're asked, how much do I rise and how much do I run? So rise over run. So we can think about slope like that. Another way to think about slope is as m, change in y, over change in x. And basically what this means is you subtract your y values of your points over the difference in your x values. So if we look at, let me draw this a little bit better. Let's draw this a little bit better. So maybe we have this point right here. And actually, maybe we'll do it like this. Let's say I have this point right here and this point right here. Rise over run. Well, this point it has an x value, I call it x1. It has a y value, I call it y1. The second point, since it's point number 2, I guess, I call it x2, y2. So when I'm finding rise over run, how much do I rise, how much do I run, what I'm really doing is I'm using this formula. Change in x, y2 minus y1, divided by the change in y, y2 minus y1 over the change in x, x2 minus x1. And that's going to give me my slope, or my rate of change. Another way to think about it is it measures the steepness of a line. So, we have, let me erase this. We have positive and negative slopes, and we have zero slope and undefined slope. But positive slope is a line such that you can think of yourself walking up a mountain. So this is up a mountain. Just imagine yourself on a line. Am I walking up or down a mountain? And that's going to tell you whether your rate of change is positive or negative. On the other hand, a line that looks like this, that slopes downwards, has a negative rate of change because here we're walking down a mountain. So that's one way to think of it. And then, of course, zero slope is just basically flat. So this is zero slope, and, we're not walking up or down a mountain. We're just kind of on this flat terrain. So slope measures the steepness. So if we have 2 positive slopes, if we have a slope like this, so this is slope 1, mountain 1, and I have a slope like this. So this is slope 2. So the question is, which of these is steeper? Which of these is going to be harder to climb up? Is it going to be this one? Or is it going to be this one? Well, it's going to be this one. This is the steeper one. And steeper means that the slope is larger. So that's what I mean by the slope measures the steepness. Another way that we can think of slope, usually when we talk about real world graphing problems, a lot of times we are going to have the time on the x-axis. And so what this amounts to in terms of linear functions is how fast is something changing over time. So that's a fourth way we can think about slope. So let's do some examples where we actually calculate the rate of change, aka slope, between the 2 points. Well, we had this formula. We had that the slope equals the y value of one point minus the y value of another point over the x value of the first point, or y2 minus y1 over x2 minus x1. So we can call this one x1, y1, x2, y2 could be the second point. And it doesn't matter what point you call point 1, point 2, but you can't mix and match. You couldn't, for instance, you couldn't say x1 is equal to 1 and y1 is equal to 4. No, it doesn't work like that. You have to be consistent. If you say x1 is -1, then y1 has to be 4. All right, so using the formula, we have y2, just plugging it in here, minus y1 over x2 minus x1. And here we're getting 2 on top, -2 on bottom. When I simplify 2 over -2, I get -1 is my rate of change. That's my slope. So is this up the mountain or down the mountain? Well, it's down the mountain because it's negative, right? So it's going to look something like this, right? All right, what about this next example? Well, if I call this point 1, x1, y1, this one x2, y2, just using my formula, I have m is equal to y2 minus y1 over x2 minus x1. Simplify this guy out to get -9 over -4. And these double negatives, when you divide by a negative by a negative, it turns to a positive. So my slope is positive 9 over 4. Positive slope means that if I put a guy on here, he's walking up the mountain. All right, so that's a little review on slope. Now, something interesting about lines is that no matter what 2 points you pick on the line, no matter what 2 points, the rate of change is always going to be the same, right? So, for instance, look at this line, 5x plus 1. Check it out. We have a point right here. This is the point 1, or sorry, that's not 1. That's the point 0, 1. Right? x1, y1. That's a point. We can pick another point. How about, I don't know. Let's see. Let's just make a little table real quick. How about we pick the point x equals 1. So when x is 1, y is 6. So that corresponds to this guy right here. So this could be our second point. x2 is 1, and y2, our output, is 6. And so we can do rise over run. So rise over run. And we can see that, the slope is going to be 5 here, right? Because we are rising 5. So this is our rise. So we're rising 5, and we're running our x value. We are running positive 1. So 5 over 1 is 5. Our slope is 5. We can also see it, if you guys remember y equals mx plus b form, we can see that m is 5. All right, cool. However, if we pick another point, let's say something that's like, I don't know, some crazy point. Let's do, I don't know, maybe something way off the graph. Like, what about if x equals -10? That's not even on the graph. Can you see that? X is equal to -10 isn't even on that graph. So if I put this in my function, when I plug in -10, I'm going to get -50 plus 1. Wow, I can't do simple math right now. That's -49, all right? -50 plus 1 is -49. Beautiful. All right, so I claim that the slope, that the rate of change between those 2 points is going to end up being 5. And we can see it with the formula, because obviously we can't do rise over run here because it goes -10, -49 goes off the graph. But let's use the formula. We have x1, y1, 1, 6, x2, y2 could be -10, -49. And when I use my formula for slope, y2 minus y1 divided by x2 minus x1. So this is going to give me -55 over -11. when you divide those negatives, look at that, we get a slope of 5. It's pretty cool, right? So that's what's super special about lines, linear functions. No matter what 2 points you pick on that line, the rate of change between those points is always going to be the same. So let's talk about what this means in a real world context, because I keep throwing around rate of change, points on a graph. Like, what the heck does that mean in the real world context? Well, suppose we have a graph like this, where our x values are in minutes and our y values are temperature in Fahrenheit. And what we want to do is figure out what's going on with this graph and see what the slope tells us. Now, the slope, you couldn't figure out what rise over run is. You can just see what, 190 minus 50 is, and then and see what the difference between 3 and 2 is. Or you can use the formula. So if I call this guy x1, y1, then I'll call that one x2, y2. And using my formula, y2, 190, minus y1 is 150, over x2 is 3, minus x1, just 2. Now, I'm going to go back, and I'm going to put my units in here, okay? 190 what? All right, y2, 190 what? Well, look, our y values are in Fahrenheit, degrees Fahrenheit. So this is going to be 190 degrees Fahrenheit minus the other y value is 150 degrees Fahrenheit. All right, all divided by, well, what's my x going to be in? My units for x are in minutes. All right, it's change in y over change in x. So this is going to be over 3 minutes minus 2 minutes. All right, y2 minus y1 over x2 minus x1 with the units. Now, what is this telling me? So on top, I end up getting 40 degrees Fahrenheit. And on bottom, I get 1 minute. And the question I pose for you all is, what does this mean? What does this mean right here? This rise over run that we just found. 40 degrees Fahrenheit per minute. Well, what this means is, for each minute that passes, the temperature goes up by 40 degrees Fahrenheit. So that's what this means. Now, if this were to be a negative 40, that would tell us that the temperature is dropping 40 degrees Fahrenheit per minute, okay? And this is constant. This is a constant rate that this thing is increasing by 40 degrees every minute. So that's one example, one real-world example of slope or rate of change. So another example of a real-world linear function when you have a constant rate of change is the amount of money that you're spending buying multiple items at the grocery store. So let's say that you're really craving some cookies, and the cookies are $2 a piece. And so this function that I have right here, this linear function, is the cost, how much you're spending basically, as a function of the cookies that you purchase. And it's linear, right? Because the rate of change is constant. So let's look at what the rate of change actually is in terms of units, or the slope. So on our y-axis, we have the cost in dollars. So if we try to find the slope of this line, if we do rise over run, we can certainly do that. If we use the formula, we can do that as well. So the rate of change here, if we start with this guy being y2 and this guy being y1, well, we have $4 minus $2 divided by x2, which is 2 cookies, right? Because our x is cookies purchased. So 2 cookies minus our x1 value is 1, minus 1 cookie. And so what we end up getting is on top we get $2, on bottom we get 1 cookie. So this is your rate of change, or your slope, $2 per cookie. So as the cookies increase by 1, your total cost is going up by $2, and that's a constant rate of change. That's what that means. So that's another real world example of slope. Anytime you go to the grocery store and you're buying something in bulk, just think about think about slope, think about rate of change, and how that can be applicable there. So why am I reminding you about all of this? Well, in this class, and if you take calculus, we're really going to get into this, but we look at a lot of nonlinear functions because life isn't always just, life isn't linear, right? It's crazy. We have ups and downs, and I don't mean to get philosophical here, but seriously, most things can't be modeled with a line, So typically we have functions that look a little bit more like this. This is how life really is. It's really more nonlinear than linear, if you ask me. And the slopes, or the rate of change, is not constant. You can see that as you travel along this curve, if you were to draw these tangent lines, these lines that touch the curve at one point, you would see that the slope is constantly changing, right? And that's the difference between a function like this and a function like this. The rate of change is always the same. If you buy 100 cookies, you know exactly how much you're going to spend, right? That's what this linear function, that's why it's so easy to work with. But here, it's like, we have this function and the slope is constantly changing depending on where we are on this curve. It's changing at every point. And so that is, that it's telling us a story here. And we're really going to talk about this more towards the end of this lecture, but you can see here that on my x-axis we have time. And that's usually a good way to think when you're thinking about slope. You're thinking about how fast something is increasing or decreasing. And in this case, we're thinking about how quickly we're earning money over time. And you can see that, it's changing. We're not earning money at a constant rate. Between year 1 and year 2, look, we're earning money really quickly at first. The slope is a very steep line. Like, we have a very steep line. So very high slope, the rate of change is high. We're earning money very quickly with respect to time. Whereas it starts to kind of flatten out. Yeah, we're still earning more money because we're rising, right? And that's the Y value, is the money earned. Yes, we're earning more money, but it's starting to slow down. The rate at which we're earning money is slowing down. And you can see that because the slopes are starting to flatten out, right? Then we move from year 2 to year 3. And maybe this wasn't a great year for the business. I'm just speaking about a hypothetical business. Because we start moving down, which means the money that we're earning is decreasing, right? And it starts decreasing. The rate at which it's decreasing is smoothing out, though, right? Because the slope here is fairly negative, whereas the slope right here is still negative, but not as negative. So that is how we can think about slopes of nonlinear lines. Is, we think about the tangent lines and how they're constantly changing. But we're going to get more into this later on. I just kind of wanted to show you that, the rate of change for nonlinear functions is constantly changing, which is a wild idea, but more on this later. So the next thing I want to talk about is concave up and concave down. We say a function's concave up if the slopes are increasing as we move along. And you can think about this as a happy face. So like if you have part of a happy face or a full happy face, we can say this is concave up, right? And we can see that in the picture here. So the slopes are increasing. We start here, right? And the slope is negative slope. Then it goes to a zero slope. Then it goes to a positive slope, and it's, getting more and more positive. It's getting steeper and steeper, which means that the slope's getting more positive. So we can see that as we travel along the curve from left to right, the slopes are increasing. That's what concave up means. And a more informal way of, an even less informal way of thinking about it is if we have a smiley face. Sorry, that's the way I think about it, the smiley face and the frowny face. Okay, so concave down is the opposite, basically. We have a frowny face, not good. So we say a function is concave down if the slopes are decreasing as time goes on. So when I say time, I typically think of the x-axis being time, just to make sense in my head. It's obviously not always going to be time, but you can see in this example, as we're moving along the curve, as time goes on, the slopes are decreasing, right? We go from a positive slope to a zero slope. That's the flat line there. Oops. Moving along. And then we start to go negative, right? We can see that this slope, we're going down the mountain, negative slope, and it gets even more negative as time goes on. So that's concave down. All right, on which intervals is the function concave up and concave down? And we're going to have to estimate because we don't exactly have the tools in our toolbox yet to get precise intervals. You will when you take calculus, but for now we're going to estimate. So what I'm going to do is I'm going to first mark off the points where it looks like the concavity is changing from up to down or down to up. So what we call this is an inflection point. And I'm going to mark these on the graph. So when the concavity changes from up to down or down to up. So let's just kind of estimate where that would be on the graph. Well, if we start at the left, it looks like we're concave down up until maybe this point. So like this looks like a point of inflection. And then perhaps this guy is a point of inflection where it goes from concave up to concave down. And let's see where else. I would say maybe this point. That's good enough. Okay, so let's write this out mathematically. When I talk about intervals, I mean x values, okay? This is important. So when I talk about where is the function concave up and down, I only care about x values. Don't tell me about y. So we start from the left. So what's happening, is this a frowny face or a smiley face? This is part of a frown. So we say this thing is concave down from x equals negative infinity, right? Because that's the lowest value that this thing's going, indicated by that arrow, all the way up to x is equal to -1, that inflection point where it starts to smile. Okay, so, all right, so let's move along. So concave up. So we're moving along the curve. We're at the inflection point, and we can see that we're smiling from x equals -1 to x equals 2. And without going too deep into this, we don't include the points because technically those points of inflection are not concave up or down. It's really where the concavity changes. So that's why we use parentheses here. Just a little side note. All right, so we moved along the curve there, concave up, and now we're at x equals 2, and we can see that this thing is frowning again. Darn. This thing is frowning, okay, and it's frowning from x equals 2 to x equals 6, and then it starts to smile again. All right, so concave down. We're going to union this with from x equals 2 to x equals 6. Beautiful. Then it starts to smile again. Life is good for this curve. We are smiling from x equals 6 all the way to x equals infinity. So we're going to union this guy with x equals 6 to x equals infinity. And that's how we determine where a function is concave up and concave down. And again, we're just estimating. We don't know if these are truly the points of inflection, but if you take calculus with me, you will find out exactly where those points are. All right, cool. Let's do this one. So the first thing I'm going to do is I'm going to mark off my perceived points of inflection where this thing starts to frown from smiling or smiling from frowning. And if I start from the left, it looks like we're frowning, frowning, frowning up until I would say it starts to smile. See, this is why we're just estimating. It's okay if it's not exactly perfect because we're just estimating here. I would say that maybe this is the point of inflection right here. I would say that's maybe where it starts to smile. Then it's smiling, smiling, smiling up until about, I would say here. I would say this is a good inflection point for, where it changes from concave up to concave down. And then it just kind of frowns all the way. So let's go ahead and write this. So let's start with concave down. Concave up. Maybe. Okay. So we're concave down. We start at the leftmost point. So this is from -infinity all the way up till that inflection point, which it looks like it's 1, 2, if this is 1. So each of these little between lines look to be like a half. So I would say this is about at -2.5. So this is x equals -2.5. I would say that's about right. Okay, great. So we're going from x equals -infinity all the way to x equals -2.5. And maybe I'm going to actually write this down here so we have some more room. Okay, following this thing from x equals -2.5, we start to smile, right? All the way to x equals 1. So we're concave up from -2.5 all the way up to x equals 1, all right? And then we start to frown again. So from x equals 1 all the way down to x equals infinity, we're frowning. So we're going to union this other this other set with 1 to infinity. So that's where it is concave down and concave up. All right, let's do this example. So this time our x values, we don't have numbers, we just have a's and b's, which, whatever, c, d, e, f, who cares? I'm going to first mark off, well, okay, so let's talk about this. If there's ever a sharp corner, that's not concave up or down, okay? So that's going to be neither of these things. Or like right here, it's not frowning or smiling, so that's neither concave up nor down in those spots. It has to be smooth. It has to be a nice, smooth smile or frown. You know, this is a crazy face. So this is not concave up nor down. Okay? So it looks like, you know, if we look at points of inflection, this isn't a point of inflection. This is not a point of inflection because we're not going from concave down to concave up. This is, I told you guys, this is not concave down. So that's not a point of inflection. We don't have to worry about that. I would say the only point of inflection that we have, you know, where we have a smooth frown to a smooth smile is probably at E. I would say that's a point of inflection. Only point of inflection here. Okay, so let's start with concave up. We can, if we start from left to right, we can already get rid of this piece, right? Because we just said that was neither concave up nor down. So really, we're starting to concave up at x equals a. We're starting to concave up at x equals a. And we follow this curve along, concave up, concave up, concave up, up, all the way until x equals 0, right? Okay, that looks good. Then we follow the curve along, and this is not concave up or down. This is just constant. We're not frowning or smiling. It's just constant from x equals 0 to x equals c. But then at x equals c to about x equals e, we're frowning. So that's concave down. So we're concave down from x equals c to about e. And then we start to concave up again from x equals e all the way to x equals infinity. So we're going to union that guy from x equals e to infinity. So we want to know, does this function appear to be concave up, down, or neither on x is less than 0? So all this means is everywhere x is less than 0 means that x is negative. And what we can do is we can look at this in Desmos. So I'm going to put x to the third in Desmos. And we can see that to the left of the black dot is everything less than 0. X is less than 0. And we can see that since that makes a frowny face, this guy is concave down for all x is less than 0. All right, so answer here is concave down. All right, here's an example. Calculate the successive rates of change for the function h of x in the table below. So what we want to do is, remember, rate of change is just slope. And we can make ordered pairs with what they're asking us. So it says find the average rate of change from x is 12 to 15. So that's these 2 points. All right, and we can write these as ordered pairs. First point is 12, 21.1. So the x and the y value, this is x1, y1. And the second point, x2, y2 is going to be 15, 21.25. All right, so that's where we're interested from x is bigger than 12, less than or equal to 15. So if we use the formula for our slope, or the rate of change, we get y2 minus y1 over x2 minus x1. I'll call this m1 for our first slope. That's going to give us 0.05. We can do the same thing for the next point. So now it says calculate the average rate of change, or the slope, from x equals 15 to x equals 18. So we're interested in these 2 points right here. The first point has an x value of 15 and a y value, or an output, of 21.25. And the second one has an x value of 18 and a y value of 21.46. This is our x2, y2. And using our formula for the slope, we get 21.46 minus 21.25, y2 minus y1 over x2 minus x1, and that's going to give us a grand total of 0.07. All right, and our final one, we want to calculate the rate of change from x equals 18 to x equals 21, the average rate of change. And they say it's average because this might not be a line. I mean, h of x, it might be something like that looks like this. So what we're doing is, if this point right here is 18 and this point is 21, we're just trying to find the slope of the straight line that connects them. That's what the average rate of change is. So anyway, side note. All right, so let's use our formula on this guy. We have our first point, 18, 21.46. It's our lower point, so x1, y1. And then x2, y2 is going to be 21, comma, what's that number in there? 21.74. All right, using the formula, get 21.74 minus 21.46 over 21 minus 18, and that's going to give us about 0.093 repeating. All right. So the next question says, based on your answers for the rates of change, is the function concave up, concave down, neither concave up, or both concave up, concave down, just based on what we found here? Well, what's happening with the slopes as the x values get bigger and bigger? That's what we want to know. So we compare the slopes, right? And we can say as x gets larger, the slopes also get larger, right? We go to 0.05, 0.07, 0.09, 3, repeating, whatever. So as x gets larger, the slopes also get larger, right? And because of this means that we are concave up. All right, so our answer here is going to be concave up. So again, as x gets larger, the slopes get larger, and that is represented by concave up. All right. So does this function appear to have a graph that's concave down, up, or neither? We're going to calculate the slopes, and then we're going to just kind of draw a brief picture. All right, so again, this is just the average rates of change, the average slopes. So I'm going to use those points. Then I'm going to use, well, actually, we'll just do this. Let's list out M1 first. So we have y minus y, so y minus y, over x minus x, and we'll calculate these later. M2 is going to be these guys. So we have y minus y, 13 minus 16, over x minus x. Our third slope, we're doing these guys. So the point 2 comma 13 and the point 3 comma 8. So y minus y, so we have second y is 8, 8 minus 13 over x minus x. And finally, our fourth slope is going to be these guys. So the point 3 comma 8 and the point 4 comma 1. So y minus y, y minus y over x minus x. All right, so computing all of these, we end up getting, for the first one, we get -1, and then we get -3, -5, and -7. So how are the slopes changing? How are they changing? Well, the slopes are getting smaller as we go on, right? So what we can say here is, as we move along, as t or x, whatever you want to think about it as t gets larger, what's happening to the slopes? The slopes get smaller. The slopes get smaller, right? We could sketch this if we wanted to see what's happening here. Knowing these points, we could just do a really rough sketch here. So here's our t-axis. Here's our f of t acting like our y. And the first one is the point 0 comma 17. So let's say this is 0 comma 17. Then we have t equals 1. Then y is 16. So maybe like this. When t is 2, y is 13. So we can kind of see what's happening here. This is 13. When t is 3, y is 8. And this is just a rough sketch. You guys, I know it's not the prettiest, but you can kind of see what the trend is, right? So this sort of looks like a frowny face, concave down. So as x gets larger, the slopes get smaller. That's concave down. All right, let's talk about increasing and decreasing functions. Increasing is when you follow a function, when you follow a curve with your pencil, the y values are getting higher, right? Basically, you're increasing in height is what an increasing function is. And decreasing is when you're decreasing in height. And we can see that decreasing can either be concave up or concave down, right? Just depending. So let me show you what I mean by decreasing. We always start to the left when we start talking about increasing, decreasing, and all that stuff. So the leftmost point on the curve, and as we move along, what's happening to the height? Is the height increasing or decreasing? Well, the height is decreasing. That's why the function's decreasing. Same thing here. If we start at the leftmost point and we move along the curve, what's happening to the height? Is the height increasing or decreasing? It's decreasing. On the other hand, with increasing functions, we start at the leftmost point, and as x gets bigger and bigger, the height is also getting bigger. So the height is increasing as we move along. Same thing with this example down here. As x gets bigger and bigger, the height also increases. Where is this function increasing and decreasing? So we start from the leftmost point, which looks like it's going off the graph. So it looks like it's increasing from -infinity all the way up to 0, and it kind of flat lines a little bit. So this thing is increasing from negative infinity, x equals negative infinity, to x equals 0. It kind of flat lines. It doesn't really look like it's increasing or decreasing here. But then it starts to move up again, all the way off to x equals positive infinity. So we're going to union this with 0, but not including 0, to positive infinity. So that is where it's decreasing. It's not increasing. It is not decreasing at all on this domain from negative infinity to positive infinity. All right, let's look at this example. So here we have a velocity versus time graph. We want to know where is this function increasing and decreasing. So if we start the leftmost point, that looks like x equals 0. We climb, and then the height kind of is static right here, right? Okay, so what's our first increasing interval? So we're increasing from x equals 0 to x equals 10. And then it starts to flatline, right? And so it starts to flatline up until this point. Then it starts to dip, and it's dipping steadily until we get to x equals 40. So what is this point right here? It looks like this point is x equals 15. So it's decreasing from x equals 15 to x equals 40. Right? This whole section right here, it's decreasing. Then it starts to increase again. So it's increasing from x equals 40 all the way, and it doesn't have arrows, so we'll just say that this thing is going to stop at 55, at x equals 55. All right, so let me ask you another question. Where, on what intervals, is this function constant? Meaning that the height is not changing. Well, it looks like there's only one place where it's constant, and that's going to be this guy right here. So this is between x is 10 and x is 15. It's constant. Where is the function increasing and decreasing? Well, we start at the left, and it looks like it's increasing all the way from x equals negative infinity up until this point right here. So increasing from x is negative infinity all the way to a. Looks like a. Okay, then at a it starts to dip off, so the height's getting smaller and smaller as time goes on, and it's decreasing until x equals b. So it's decreasing from a to b, our x values, and then it starts increasing again. It starts increasing at b all the way up to x equals 0. So we're going to union this from b to 0. Okay? It looks like it's constant from 0 to c, but then at c, it starts to increase again until we get to d. All right, the height is increasing from c to d. So we're going to union this from C to D. And you can kind of see that here, I hope. Then it starts to dip off again from D. And it starts to dip all the way to F. So we're going to union this decrease with D. X equals D to X equals F. All right, and then it starts to increase from F to positive infinity. So the last union we have, we're going from F to positive infinity. Now let's talk about where is it constant. I don't have this on here, but let's talk about it anyway. It's only constant where the height remains stable. So it's constant from x equals 0 to x equals c. The height doesn't change. Okay, so for this problem, we want to investigate the concavity of this graph as well as where it's increasing, decreasing, and constant. So we want to first estimate our inflection points, or where it changes concavity. And we can see that it looks like it's going from concave up to concave down right about here at x equals -1. Then it's concave down and it starts to concave up at, I would say, approximately x's 0.5. So it looks like those are only points of inflection here. So let's also, let's see. So I'll do concave up in blue. So where is it smiling? Well, it looks like it's smiling right here. Right, so concave up. And then we also have this little area that's concave up. So I'll do this guy in blue as well. And then this guy, I'll just leave in purple, concave down. So we have purple is concave down, and we'll say blue is concave up. All right, so out of the areas where this thing is concave down, so in this purple region, which part of the region is also increasing? Where's y getting larger and larger? Where's the height increasing? Well, it's increasing. Let's do that in green. It's increasing from this guy all the way up until we reach the peak, and then it starts to decrease. So it looks like it's increasing from x equals -1 to x equals 0. So where is it increasing concave down? We say from x is equal to -1 to x is equal to 0. And it looks like that's the only interval we have here. Where is it increasing and concave up? Well, now we look at our blue regions. And we can see that, if we follow this curve, it's actually decreasing here. So it's decreasing from -infinity all the way to about, I would say, x is -1.5. And then it starts increasing. So, okay, so that portion, it's increasing from x is -1.5 to about x equals -1. And it's also concave up. Then we look at the other blue portion all the way to the right, and we can see, if we start at x equals 0.5, we can see this thing is decreasing, decreasing, decreasing until about x equals 1, and then the height starts raising again. So it's increasing from x equals 1 to x equals 2. Okay, so we're going to union this from x equals 1 to x equals 2. Decreasing and concave down. Well, the only other part where it's concave down is this purple region, and we can see that the height is getting lower as x moves on. So this happens when x is equal to 0, from 0 to approximately x is equal to 0.5. Decreasing and concave down. What about decreasing and concave up? Well, that is going to be this guy right here and this guy. That's decreasing and concave up. Because we still have a smiley face, but as x goes on, y gets smaller. All right, so that's what that means. So decreasing and concave up is going to be from negative infinity all the way to x is equal to negative 1.5. And we're going to union that with x is equal to 0.5 to x is equal to 1. All right. And the last one is where is this thing constant? Well, it's just going to be this guy right here. We're starting at x equals 2, and we can see the height isn't changing all the way off to infinity, indicated with this arrow. So it's going to be constant from x equals 2 to infinity. So let's look at this graph. We have y equals sine of x. And maybe you haven't heard of sine of x since geometry, but when you take trigonometry, you'll learn how to graph these things. All right, so let's go ahead and mark off our perceived inflection points first. It looks like we're going from concave down to concave up right here at x equals negative pi. And it looks like we're going from concave up to concave down at x equals 0. And then concave down to concave up again at x equals pi. So let's see, what did we do? Concave down was purple, so let's keep it like that. We'll do purple is concave down, and we'll do blue is concave up. Okay, so in purple we have this guy, concave down. All right, and this guy. And then in blue, we have concave up right here. Concave up. And I don't have any arrows at the end, so I'm just going to assume that this is going to end there. All right. So where is it increasing and concave down is our first question. Well, if we look at the concave down part, it appears to be increasing if we start our leftmost point from x equals negative 2 pi all the way up to x equals negative 3 pi over 2. And also, so negative 2 pi, x is negative 2 pi to negative 3 pi over 2. And then we'll union that with this guy. We're going from x is equal to 0 to x is equal to pi over 2. That's where the height's increasing. Okay, so those are our intervals of increasing and concave down. Where is it increasing and concave up? Well, we're going to look at our blue portions, and it doesn't look like so the height doesn't start to increase, it looks like, until x is negative pi over 2. And then it increases all the way up till x equals 0. Right? So increasing and concave up, we're going from negative pi over 2 to 0. And then we're going to union it. So it also appears to start increasing in height when x is equal to 3 pi over 2, all the way up to x equals 2 pi. So that's increasing and concave up. Decreasing and concave down. We start at negative 3 pi over 2, and then the height starts decreasing until negative pi. Concave down, that is. We have to have that in our category as well. So this is negative 3 pi over 2, all the way to negative pi. And then we'll union that with, again, it's concave down from pi over 2 to pi, and it's also decreasing there. So we'll union that with pi over 2 to pi. Okay, decreasing and concave up, we can see starting at the blue portion that's left here, we are decreasing from x equals negative pi to x equals negative pi over 2. And then we start to decrease again, starting at x equals pi to x is equal to 3 pi over 2. Okay, so here is a chemistry application of rates of change and concavity. So we have this table that's showing the quantity of carbon-14 in micrograms in a 200 microgram sample remaining after t,000 years. We see from the graph that Q is a decreasing function of t, so its rate of change is always negative. What can we say about the concavity of the graph, and what does this mean about the rate of change of the function? So let's first analyze this table. Okay, so here this is our input, t thousands of years. This is acting like our x. That helps you remember it. And this is our output. This is how many micrograms of the carbon-14 is left after t,000 years. And we can think of that as our y. And then we have our rate of change, delta Q over delta T, which is basically just the change in y over the change in x. You can think of it like that, the slope. Okay, so we can see from our little chart here that the rate of change between these 2 points, 0, 200 and 5, 109 is negative 18.2. So we can just write a little note here. This is the slope of 0, 200 and 5, 109. All right, and we see that it's a negative slope, just fine. And then for this next set of numbers, we have the slope is negative 9.8. So this is the slope, the average rate of change between 5,109 and 1060. Slope of that line that connects those guys. And finally, the slope of the line that connects these last 2 points is negative 5.4. All right, cool. So now that we got that, we can look at the graph, right? So I can see that my first ordered pair is 0, 200, as we can see from the graph right here. It's our first ordered pair, and that's indicated there. Then we have the next ordered pair, 5, 109, etc., etc. So I've listed those 4 ordered pairs in gold, those little gold points. And what we can see, what this graph is showing us, is that yes, the amount of carbon-14 is constantly decreasing, right, as the years go by. However, it's decreasing faster at first, and we can see that here. There's a larger jump between this point and this point than there is later on between year 10 and year 15. So we can see that yes, the slopes, if we notice what's happening to the slopes are increasing, right? And that tells us that our graph is going to be concave up, right? This is the slopes. The slopes are increasing. And again, even though the function is a decreasing function, this thing is still concave up, right? Because we can see that the larger decrease. So let's actually write this down. So let's kind of summarize what's happening in this graph here. So from 0,000 years to 5,000 years, the amount of carbon-14 is decreasing quite quickly, whatever that means. All right, there's a big drop, right? There's a big drop from year 0 to year 5. As the years go by, the amount of carbon-14 is decreasing, just not as quickly. This is the key thing here, not as quickly as before. So we can see that from year 10 to year 15, yes, it is decreasing, but the decrease is much smaller than this big drop in the beginning. Okay, so that's what we can say about this curve. Did they want us to mention anything else? So we talked about concavity. It was concave up because the slopes are increasing as time goes on. And, right, okay, so good. We talked about this. So this is the real world interpretation of this graph. All right, so this table is giving us the distance traveled by a cyclist as a function of time. We want to investigate the concavity and then talk about the speed, which is the rate of change of the distance with respect to time. So here, if we look at our little chart, we can see the input is our time, and so this we can think of as our x value on our x-axis, and d, our distance, is our output in miles. And so that's telling us that our slope, if we were to calculate the slope of between any of these points, our units would be in miles on top, right, for y, over hours, right? So our slope is in miles per hour, which should be familiar. That's speed. Okay, so what is this telling us? Well, it's telling us that between 0, 0, and 120, our slope is 20. All right, our speed is 20 miles per hour. Then for this guy, right, this is telling us between 1 hour and 2 hours, the slope is 15 miles per hour, and so forth, right? Keeps going on like that. So what's happening to the speed as time goes on? Well, the speed is decreasing, right? Which means the slope is decreasing. The rate of change is decreasing, which tells us this thing should be concave down, right? This is concave down because the slopes are decreasing as time goes on. And we can see that with our graph here. It kind of is making a frowny face. So, let's investigate what's happening here. So here's our first point, 0, 0, which we can see here. And our second point is 1, 20, which we can see here. So what does this represent? What do these two points represent? Well, our x-axis is in hours and our y-axis is in miles. So between 0 hours and 1 hour, it looks like the slope is fairly steep. It starts out pretty steep. So we're moving forward and we're going at a pretty high speed ish. Of 20 miles per hour. So our average speed between 0 hours and 1 hour is 20 miles per hour. We find that slope, and then we start to slow down. So from 1 hour to 2 hours, we start to slow down, and we can see that with our data here. Our average speed between 1 hour and 2 hours is now 15 miles per hour. So yes, we're still moving forward. We're still gaining miles, as we can see by the increasing function, but we're slowing down, right? We're not moving as fast as we were. So, and even we're moving even slower from 2 hours to 3 hours. We can see that we're moving at 10 miles an hour. That's our average speed between 2 hours and 3 hours. And yeah, so this is going to give us a concave down curve.